using mercury in glass thermometer. So before I come to that, we now look at cross-sectional, cross-sectional view, cross-sectional view of a mercury in glass thermometer. So from physics, mercury in glass thermometer is an example of types of thermometer. So, but mind you, mercury is a thermometric substance. So now we're going to look at how we obtain the transfer function using mercury in glass thermometer. Now, we all know what thermometer is used for. Like we know that thermometer is used to record temperature. Now, most of the times, if you want to record the temperature of a liquid, you use thermometer. So now, let's say we are using a mercury in glass thermometer. So the mercury being a thermometric substance, is already in the thermometer. So whenever you place a thermometer in a hot water or a water that is about boiling, the mercury will expand and then it will take a reading. You take a reading on the glass of that thermometer. So now we're going to look at from here now. Let's see, we're going to draw a cross-sectional view of a mercury. So now we're looking at the cross-sectional view. Now let's see, this is the diagram. This diagram. Then I have so this one that is here. I have the mercury here in the thermometer. So I have this as the temperature of the inner temperature. So let's see, we have this dotted line. Let's say here is our glass wall. You have a glass wall. So now, this one now is our film resistance. I have my film resistance. Then from here, this one that is outside, the outside one is T1. Let's say T1 is the surrounding temperature. The surrounding temperature. It's just like temperature of the atmosphere. So the surrounding temperature, which is T1. So now we're going to look at this. By the time you put a thermometer in the water that's above boiling, it will record the temperature. Then there's the heat generated in the input. They have an input heat in that thermometer because you have immersed. You're going to immerse a thermometer in a steam or fluid. And let's say that steam or fluid is about heating now, boiling. So when you immerse it, there will be an heat input. Though the atmosphere part of it, heat will not be generated, there will be no heat generated. But the inner part of the thermometer, there will be a heat generated. And that heat now will be called the heat input. So now, already we have immersed this thermometer in a steam of fluids. So now, let's say this what you are seeing on the board now is the cross-sectional view of a mercury in glass thermometer. So we have already indicated the film resistance, the mercury, the glass wall, the surrounding temperature. Now, which is the T1. We are going to look at the simplifying assumption. Simplifying assumption. So we go to one. We have to say at any given time, T. The mercury, the mercury assumes a uniform temperature throughout. Throughout. So this one is first condition, number one condition. So the thermal capacity will be attributed to the mercury. The thermal capacity or the thermal energy, or let's use that the thermal energy and the chemical symbol of mercury is Hg in chemistry. So now also need to look at the system will definitely operate at a steady state. The system will operate at a steady state. The system operates at a steady state. Operate at a steady state. Then another assumption, we see that no generation or consumption. So if you no generation or no generation through consumption. That is no chemical, no chemical what? Reaction. So since there is no chemical reaction, meaning that your generation and consumption is equal to what? Zero. So from here, we're going to look at the general energy conservation equation. So before we look at the general energy conservation equation, we're going to look at, let's say, heat heat input, or the input heat will give you HA into H now means mass transfer coefficient. A represent the cross sectional area. Then to give you the surrounding temperature, T1 minus what? The temperature here, which is T. So it will give you the input, the heat input. Then we'll now look at the heat output. Heat output will give you zero. No heat generated outside the thermometer. It's only within, heat is generated within the thermometer at the inner thermometer. And that's why you're having heat input. And the heat input will give you HA bracket Ti minus T. So now we're going to look at steady state energy equation. So we're going to look at, before we do that, we're going to look at accumulation, accumulated what? Accumulated heat. Before from here, we'll now look at the steady state energy equation. So now, accumulated heat will give you heat. Let's say we know that from physics, H is equal to quantity of heat. It will give you MC delta theta. MC delta theta in physics. Heat, H represents quantity of heat, M represents mass, C represents the capacity, change in T represents change in temperature. Now we're going to look at accumulated heat. And mind you, when you are calculating for accumulated heat, it will give you the heat that we know H equal to MC delta theta, which is MC, let's say MCP delta theta. You understand? Delta theta, let's say change in T with respect to what? you are going to divide it by the t. The t now it means you are dividing it with respect to what time. So anytime you are asked to calculate accumulation now, whatever you are going to do, you are going to divide it by time. So that's why you are going to have this way. So to give you mcp, you have it dt over small t. That's small change in t. So now from here we're going to look at unsteady state, unsteady state, unsteady state energy equation. So it will now be heat input, heat heat output will give you heat input plus heat generation, heat generation minus heat consumption minus heat accumulation. The accumulation is the accumulated heat accumulation. Now, this is what I'm going to get. This is the unsteady state energy equation. Why is it? It is called unsteady state because in this equation you have heat output, heat input, heat generation, heat consumption, and heat accumulation. So for it to be a steady state, it will be heat input will give you heat what output. For in this case now our heat output is what is zero. So now this one is already zero. So we're going to have it this way. Now let's see. One of the simplifying assumptions, we say there's no chemical reaction. And since there's no chemical reaction, both heat generation and heat consumption is equal to what? Zero. So we're going to have it this way. Is heat output will give you heat input. Then we have minus heat accumulation. So this is what I'm going to get. Minus heat accumulation. So from here now, mathematically, if you arrange it mathematically, you collect items, you're going to have it this way. Heat accumulation, or you can say accumulated heat, will give you this one. Now come over here. You're going to have heat input minus heat output. This is what I'm going to get. So but our heat input here is zero. We have but our heat input is equal to HA bracket T1 minus T. Then our heat output is zero. So now we have the accumulated heat or heat accumulation is equal to MC delta theta over T. So it's the same thing as MCP dt over the dt over the small t. So this small t now is with respect to time. So while if you divide this heat with time, it will give you accumulated heat. So now we're going to have the heat accumulation will give you mcp dt over the small t will give you the heat input will give you h a into t I or t1 minus t, then minus heat output is what? Zero. So from here now you cannot get equation now. You get an equation. So let's say this one now give you minus heat output will give you HA bracket T1 minus T. So it's equal to the accumulated heat, which is MCP the big T over the small t will give you HA into T1 minus T. So this one, let's say this one is equation 1. Let's call it equation 1. This is equation 1. So we have gotten equation now. Now, let's say at steady state, at steady state, at steady state, then your accumulation now is equal to 0. Then once your accumulation is equal to 0, and that's why you're going to always have input is equal to what? Output. So you see that's why steady state, you must have input equal to output. So like when I say for steady state equation, you must have both the input, the output energy, the input energy, the heat generation energy, you have the heat consumption and the accumulation. So you say at steady state you have accumulation equal to 0. So at steady state, so let's say at steady state, we are going to get it this way. Let's say you have MCP, you have dt, let's say dTs over dt is equal to HA over HA times T1s minus Ts. So let's say this one is equation 2. This one is equation 2. Let's say at steady state, you have, let's say you have MCP dTs over dt equal to HA into T1s minus Ts. This x represents steady state. So now, what I'm going to do is I'm going to say, okay, I see equation 1 minus equation what? 2. So equation 1 minus equation 2. So I will now have the same thing I did in the last proof. So I'm going to do the same thing here. My equation 1 is I have my MCP dt over the small t minus MC, that's for equation 2, MCP dTs over dt is equal to, then equation 1 now, here I have my HA into T1 minus T, then minus equation 2, minus equation 2, I have HA into T1s minus Ts. This is what I'm going to get. So what I'm going to do next is that I'm going to factorize this one and then open up this bracket with this minus sign here, and then do collect like terms. Now add up is and then this together. So what I'm going to do now, from here I'll see that something is constant here. I have MCP d over dt is here. I also have MCP d over dt is also constant. So I'm going to bring it out from the bracket. So I'm going to have MCP d over dt. So if I bring it out here, I'll have what? T. So here now, if I do the same thing here, MCP d over dt, I'll have Ts, say minus Ts here is equal to this one now. I have HA into T1 minus T. Then I'll have something like this, minus bracket HA into T1x minus Tx. So I've gotten the equation like this now. So the next I'm going to do is open the bracket. open the bracket. You open the bracket. From my left hand side, I have my MCP D over the T multiplied by T minus TS equal to H times T1 will give you HA T1. Then HA times T here will give you minus HAT. Then I'll use this minus sign. This minus HA times T1S will give you minus HA T1S. Then minus HA times minus TS will give you plus, because minus times minus give you plus HA TS. This is what I'm going to get. TS. So now I'm going to add up T1s together. So it will now be like collect items. I have HA T1. Then I have another minus HA T1S. I'll bring it together. So minus HA T1S. So this one now is the next one minus HAT. Then I have plus HATS. So it is equal to MCP D over dt into T minus TS. So it's equal to this. So from here, I'm going to okay, if I factorize now, this HA, I have HA here, I have H here. If I factorize, I'm going to have HA into T1 minus T1S. So then I have, then over to this point, for here, I have HA here, I have HA here. So I'll do what? Minus HA here into HA is common here. Let's say HA into T minus what? Minus TS. This is what I'm going to get. If you are forming a bracket now, this plus now change to minus. Because if you use this minus HA and multiply by dt, you are going to have minus HAT. So if you have minus HA times minus TS, this minus will change to plus here. So you're going to have HATS plus HATX. So now you're going to have MC. You have MCP. So you're going to have MCP D over dt into T minus TS is equal to HA into T1 minus T1S minus HA into T minus TS. So now I'm going to introduce derivation variables. So derivation variables. From derivation variables, I have, let's say this T minus TX will give you T prime of what? T. Then let's say here T1 minus T1X will give you big T1 prime of what? T. So this one is derivation variables. Now, so before I come to this aspect, let's say here is equation 3. So before I move to that, I now have to look at bringing back equation 3 here. I say let's equation 3, I have MCP D over dt, then into T minus Ts, then is equal to Ha into T1 minus T1s, then I have minus Ha into T minus Ts. So from here now, I say divide through, divide through by what? Ha. If I divide through by Ha, I'm going to have MCP over Ha, then multiply by d over dt into now I'm going to include these derivation variables. I have my t minus ts is equal to t prime of t. So multiply by t prime of t. Then is equal to this ha into t1 minus t1s will give you t1 prime of what? T. I have t1 prime of what? T. Then minus ha into t minus ts will give you t prime of what? T. We want to have t prime of what? T. So I'm dividing all through by ha. So that this ha will cancel each other. This ha will cancel this ha. So it will have this over ha. This over ha. So it will cancel each other. If you look at this equation now, looking at equation 3. So there is no ha here. If you cancel both sides by ha, you are going to have mc over ha times d over dt. So from here you now include those variables. So let's say here is equation 4, and then have this one is equation what? 5. So you now say what I'm going to do is I now substitute equation 4 and 5 into equation 3. If you substitute it, you are going to have t prime of t. Then here now, which is t1 minus t1s, will give you t1 prime of t. You put it here. Then t minus ts, you have t prime of t from derivation variables. So you're going to come up with this equation now. So now you have m cp over ha multiplied by d over dt times big T of t is equal to what? T1 prime of what? T, then minus T prime of what? T. You are going to come up with this equation now. By the time you divide both sides by this way, and then you apply the derivation variables, you come up with this equation. So from here, what you are doing now is derivation. I'm deriving a transfer function. Now, Cp over Ha, then this equation, I'm writing it here. They have d over dt. So this d over dt times t prime of t will give you t prime of t over dt. Then is equal to t1 prime of t minus t prime of what? T. So we're going to come up with a differential equation. But meanwhile, this one is minus t prime of t. If you bring it here, you're going to have mcp over ha. They have dt prime of t over dt. Then this one now, this minus t prime of t come here, becomes plus t prime of what? T. So here becomes is equal to t1 prime of what? T. So now something will happen. Definitely I say let this equal to mcp over ha. So now this is our time. This is our constant. So it will give you mCp over Ha. M represents mass. Cp represents the specific heat capacity at constant pressure. Then H represents the mass transfer coefficient. Then here A represents the cross-sectional area. So now, if this time constant is equal to this, that means I will have this time constant multiplied by d big T prime of what t all over the t. Then this one we have plus big T prime of what t is equal to t prime of what t1 prime of what t. So this is what I'm going to get now. Going to get this equation now. So before I do that, let's say this one now is equation. Let's call this equation 4. Let's say this one is equation 4. Equation 4 now. So now, having this equation, I want to take Laplace transformation on both sides because this is the differential equation. This is first order differential equation. So taking the Laplace transform on both sides, take Laplace transform on both sides. On both sides meaning both the left and the right hand side. So we're going to have this, which is time constant, is constant. You bring it out. Then you now take a Laplace transformation of d t prime of t over dt. Then have plus Laplace transform of big T prime of what t. Then is equal to Laplace transformation of t1 prime of what t. So I'm taking the Laplace transform on both sides. So you have it this way, both the left hand side and the right hand side. So Laplace transformation of first order differential equation, which is d t prime of t over dt will give you s t prime of what x minus t prime of 0. This is what I'm going to get. First, Laplace transformation of dt prime of t over dt. So now we are going to put it here in this equation. Then let's take our initial condition. Our initial condition as t prime of 0 equal to 0. So we'll take our initial condition as t prime of 0 equal to what? 0. So now we're going to substitute the initial condition and this Laplace transform on this equation. So we do that. We have tau, which is time constant. I'm going to multiply by Laplace transformation of this equation of this dt prime of t over dt, and I have it as x t prime of x minus t prime of 0. So I'm going to x t prime of x minus t prime of what? 0. So I substitute it. So the next one now will now have plus Laplace transformation of t prime of t. This t prime of t now will be transformed to x. So it will now be minus, it will now be plus t prime of x equal to Laplace transformation of t1 prime of t will be transformed to what? t1 prime of what? X. This is what I'm going to get. So from here, I will include my initial condition here. So I have my time constant multiplied by x t prime of x minus 0. So plus t prime of x is equal to t 1 prime of what? X. So from here, this minus this will give you tau into x t prime of x. So plus t prime of x is equal to t 1 prime of what? X. So if you use this and open up this bracket, we're going to have t x tx t prime of what? X plus t prime of what? X is equal to t 1 prime of what? X. So something is common here. You're going to come up with this equation. Something is common here, which is t prime of x is here. I also have t prime of x here. So t prime of x is common. So I will factorize. So if I factorize, I'm going to have it this way. I'm going to have the equation that t prime of x will give you t x plus what? 1 will give you t 1 prime of what? X. So now from here, what I do, I'm going to divide through by t x plus what? 1. I'm going to divide through by t x plus 1. So I'm going to have it here. I'm going to have t 1 of x multiplied by tau x plus 1 is equal to t 1 prime of what? X. So that this one will cancel this out. Tau x plus 1. This will cancel this over tau x plus what? 1. So that you're going to have t prime of x will give you t 1 prime of x over tau x plus what? 1. Is what I'm going to get. So from here now, I'll now multiply 1 over t 1 prime of x from both sides. From both sides. You multiply both sides by 1 over t 1 prime of x. You will have t prime of x over t 1 prime of what? X. It will give you t 1 prime of x all over tau x plus 1. Tau x plus 1 multiplied by 1 over t 1 prime of what? X. So that this t 1 prime of x will cancel this. So we're going to get 1 over tau x plus what? 1. So therefore, we're going to have t prime of x over t 1 prime of x will give you 1 over tau x plus what? 1. So you're going to get the same transfer function using cross-sectional view of a mercury in glass thermometer. So you're still going to have the same transfer function. So this is derivation transfer function. So thank you for listening. Be blessed.